Have you ever found yourself sort of stuck in that cycle where, every new feature, every little change you make to a project just seems to break something else?
Oh, yeah,
And it
definitely.
ends up costing way more time, more money than it feels like it should. Makes you wonder if there's a better way to build things so they actually last, right?
Right, or maybe you're just starting out on something new.
Exactly. And you're thinking, how do I lay the groundwork now so this whole thing doesn't become a complete tangled mess later on?
It's super common frustration, I think. That feeling that there has to be a more, I don't know, resilient way to do things.
Well, today we're going to try and unpack that. We're embarking on a deep dive into the very heart of software structure and design. And these are principles that they really go beyond just lines of code. They speak to the resilience of, well, any complex system, really.
Yeah.
Our guide for this is none other than the legendary Robert C. Martin. You probably know him as Uncle Bob.
Uncle
Yeah.
Bob, yeah.
And we're looking at his seminal work, Clean Architecture, a craftsman's guide to software structure and design.
And what's so compelling here, I think, is how universal these ideas are. I mean, yes, they come from software engineering.
Right. Deeply rooted there.
But Uncle Bob's insights, they offer these timeless lessons for organizing, well, pretty much any complex system you can think of. A business, a product design, maybe even just getting your personal workflow sorted out.
That's a great point.
So our mission today really is to pull out those core nuggets of knowledge, understand why these principles matter so much, especially now, and figure out how they can help us avoid that dreaded programming hell.
Programming hell. Yeah, I've been there.
We all have. It's about ensuring adaptability, longevity for whatever system you're building, making it truly soft, inherently easy to change and evolve.
So for this deep dive, we've basically curated insights straight from the book. We're covering everything from the basic definition of architecture,
Yeah, fundamentals.
the evolution of programming paradigms, those crucial, solid principles everyone talks about. And we'll even get into some really fascinating stories, sometimes cautionary tales, from Uncle Bob's own career. 50 years of this stuff.
Half a century, yeah. It's incredible.
Think of this as your personally curated shortcut, getting you well-informed on this critical topic, getting the essence of decades of wisdom, hopefully distilled into something practical.
So why should you, listening right now, care about all this, these kind of technical details?
Good question.
Because honestly, by grasping these foundational concepts, you get more than just like a deeper understanding. You get the vocabulary, you get the framework to actually identify robust designs.
Right, to spot the difference.
Exactly, to ask those really sharp, critical questions, to challenge assumptions that, might otherwise lead you down a path to really costly mistakes down the line. It's about having those aha moments, the ones that empower you to make more informed decisions, to steer your projects towards long-term success, and frankly, to foster real professionalism in whatever you do, not just for today, but, for years to come.
Okay, let's start with this this paradox that Uncle Bob points out right near the beginning of the book. It's about the unseen cost of a mess, the sometimes staggering cost.
Right.
He talks about when he first started programming back in 1964. Can you imagine?
Wow, 64.
Yes.
Yeah.
He was working on these machines the size of refrigerators.
Uh-huh, yeah. Big iron.
With just 4K of core memory and half megahertz cycle times.
Tiny numbers by today's standards.
Absolutely tiny. Fast forward to today, he's writing his preface on a MacBook. 4 i7 cores, 16 gigs of RAM, a terabyte SSD.
It's just orders and orders of magnitude different.
It's almost unimaginable, isn't it? He calculates the difference in computational power is something like 10 to the power of 22, which, he says, is equivalent to the number of angstroms from Earth to Alpha Centauri. Just mind-boggling scale.
That's a great way to put it in perspective.
But here's the kicker. Despite that insane leap in hardware power, the underlying stuff of software,
Yeah.
those basic if statements, assignment statements, loops, fundamentally, it's still the same.
That hasn't changed.
It hasn't changed at all. And that's a really profound observation, I think.
It is.
All this astronomical hardware evolution, but the basic building blocks, static, and this sort of enduring nature of our tools, it underpins the timelessness of these architectural rules we're going to talk about.
Exactly. If the core elements are constant, then the principles for putting them together in a sensible way, they should also be pretty universal.
Should be timeless, regardless of the latest framework or buzzword.
Yeah, absolutely. And this unchanging core, that's precisely where the signature of a mess starts to show up. And you see this pattern way beyond just software, really. Uncle Bob shows these really compelling figures in the book, charts that just vividly depict what happens when systems are just, thrown together in a hurry.
Yeah, the move fast and break things approach, maybe?
Kind of, yeah. But maybe just move fast, where you prioritize sheer output over, like, cleanliness and structure. And what happens? Initial productivity starts high, maybe close to 100%. Looks great.
It's amazing at first.
But then, release after release, it just plunges. It heads towards zero.
Wow.
Imagine the frustration there, right?
Yeah.
Developers working harder than ever, putting in overtime, really dedicating themselves. But their actual output keeps going down.
So all their effort is just managing the mess.
Exactly. Just managing the complexity, moving stuff around, trying to squeeze in one more tiny feature.
That sounds exhausting.
It is. And from, say, an executive's perspective, the financial side is even scarier. He shows how monthly payroll can just skyrocket, maybe a few $100,000 for the first release.
Okay, reasonable.
Up to $20 million by the 8th release. And for that $20 million, you're getting almost nothing in new functionality.
Ouch. Any CFO looking at that chart would be hitting the panic button.
Absolutely. They demand immediate action. And the bigger connection here is so important. This isn't just a software problem. It's a fundamental project management issue, a business sustainability issue.
Right. It applies anywhere.
Any field that consistently prioritizes just speed over structure, that neglects the foundational organization of its work, it will see its initial velocity just grind to a halt. It gets crushed under the weight of its own complexity. You might feel really productive now, shipping features left and right.
Yeah, getting that dopamine hit.
Exactly. But you have to ask, what mess are you unknowingly creating that's going to consume all your effort and budget later on?
That is a really powerful point about those hidden accumulating costs, and it leads right into what Uncle Bob calls the hare and tortoise lie.
Ah, yes, the fable.
Right. The common idea, the fallacy, is that writing messy code lets you go fast in the short term. Okay, maybe it slows you down later, but you get that initial speed boost.
We'll clean it up later.
Exactly, we'll refactor later. But he just flat out says this is a bigger lie. He claims making messes is always slower than staying clean, no matter which time scale you're using.
Always slower. That's a bold claim.
It is pretty provocative, isn't it? It pushes back hard against that really common belief, especially in startups, We just have to get to market first. We can clean it up later.
The pressure is real, though.
Oh, the pressure is absolutely real. But his point is, market pressures never abate. They don't go away once you launch.
Right. Then you have competitors.
Exactly. A horde of competitors is suddenly on your tail, demanding even faster development. So later just never arrives.
Makes sense.
And he actually cites this experiment by Jason Gorman, really interesting. He found that test-driven development, TDD, which is a discipline focused on cleanliness,
Right, writing tests first.
was consistently faster. Not just in the long run, but every single day, even within these short 30-minute coding tasks.
Wow. Even on that micro scale.
Yeah. So that creeping mess of code, it just relentlessly drags down your productivity. It's like this invisible friction on everything you try to do.
Okay.
And the idea of just throwing it all out and starting over, redesigning the whole system.
The big rewrite.
The big rewrite. Uncle Bob says that's just the hair talking again. It's the same overconfidence that got you into the mess in the first place.
So what's the alternative?
His conclusion is simple, really. The only way to go fast is to go well.
Go well. I like that. Which brings us to this really fundamental idea about software's true value. We need to rethink what we're actually delivering.
Okay.
Software fundamentally gives you two distinct kinds of value. The first one is obvious. It's behavior. The features, the functionality it provides, how it makes or saves money for people.
That's what users see, what stakeholders usually ask for.
Exactly. It's the most immediately apparent value. But the second value, and Uncle Bob argues this is the greater value, is its architecture.
Its structure.
Its structure, its resilience, and crucially, its softness. That inherent ease of change.
Softness, meaning flexibility.
Yeah. Flexibility, adaptability. Think about it at the extreme. If you give me a program that works absolutely perfectly right now,
does exactly what I want,
but it's totally impossible to change, locked down solid, the moment the requirements shift, even a little bit.
Which they always do.
They always do. That program becomes useless because I can't adapt it.
Right. Dead end.
Now, flip it. If you give me a program that, okay, maybe it doesn't work perfectly right now, maybe it's buggy,
Yeah.
but it's incredibly easy to change. The structure is clean.
Okay.
Well, then I can fix it. I can make it work. And I can keep it working as requirements continue to change and evolve. That program remains continually useful.
So the adaptability is actually more valuable than the current snapshot of functionality.
In the long run, absolutely. This totally shifts your perspective, doesn't it? From just immediate features to long-term adaptability as the real measure of a system's worth.
Yeah, it does.
A system that can't adapt, that can't evolve, is ultimately a dead system. No matter how perfectly it worked at one point in time, the real power of software isn't just what it does, but its capacity to keep doing it by being flexible enough to meet future needs. And that insight applies way beyond code. It's critical for anyone building anything complex that needs to last.
Building on that distinction, that idea of two values, Uncle Bob brings in this brilliant analogy. He uses President Eisenhower's famous matrix.
Ah, the urgent, important matrix.
Exactly. Eisenhower apparently said, I have two kinds of problems, the urgent and the important. The urgent are not important, and the important are never urgent.
Classic quote. Very true.
And in software, it fits perfectly, doesn't it?
Yeah.
Shipping that new feature, fixing that critical bug. It often feels really urgent and important, top priority.
Absolutely. Firefighting mode.
But many features, while definitely urgent to stakeholders, might not actually be architecturally important. They don't affect the long-term health.
Right. They're superficial sometimes.
Whereas the architecture, the underlying structure, that's undeniably important for the system's longevity, its adaptability. But it rarely feels urgent.
Nobody's banging down your door demanding better architecture today.
Exactly. There's no immediate fire drill for refactoring a core module. And this mismatch explains why architecture so often gets neglected, doesn't it?
It does. Business managers, quite naturally, are focused on the urgent. They're not equipped to evaluate the importance of architecture. Their priorities are features, deadlines, immediate ROI.
So it falls to the developers.
It absolutely does. It becomes the responsibility of the software development team to assert the importance of architecture over the urgency of features.
So you have to be the advocate.
You have to be the advocate for the system's long-term health, for its future flexibility.
Yeah.
Even when that means, pushing back a bit on those short-term demands.
It takes courage sometimes.
It does. And you need to be able to articulate why that structure matters for the business in the long run.
Because if architecture always comes last,
if it's always deferred, always pushed off in favor of the next urgent feature, the system just inevitably becomes prohibitively costly to develop. Change becomes harder and harder, eventually grinding to a halt in some areas.
the system calcifies.
Exactly, becomes brittle. So the crucial question is, who's fighting for your future flexibility? Who's advocating for the long-term health of the project when all the immediate pressures are screaming faster, faster?
You have to be the architects, the developers.
It's their crucial role. It's a professional responsibility, really, to champion the importance of structure, because without it, the project's true costs will inevitably spiral out of control. Not because of bad coding necessarily, but because of a fundamental failure in foresight and design.
Okay, so if we accept this idea, this fundamental value of architectural flexibility, that it's paramount, what does that actually mean for how we build software? How do we achieve that flexibility?
Right, the practical side.
Yeah. And Uncle Bob takes us on this really fascinating historical tour of programming paradigms. And his point is, they primarily introduce timeless disciplines. They're not necessarily about adding new capabilities.
Interesting take.
Each one, in essence, taught us what not to do to avoid common mistakes and build more robust systems.
So less about power, more about constraint.
Exactly. Constraint as a path to better design. Let's start with the first one, structured programming.
Okay, the classic.
This paradigm, he says, is discipline imposed upon direct transfer of control. Basically, reining in the chaos of arbitrary program jumps, like the go-to statement.
Ah, the infamous go-to. Yeah, its roots go way back, even to Alan Turing's theoretical work. But it really gained practical steam with Ebbsford Dijkstra's work in the 60s.
Dijkstra, a giant in the field.
Absolutely. He was really concerned about the lack of, scientific rigor in programming back then. Errors were everywhere. Proving code correctness seemed impossible.
Kind of the Wild West.
Very much so. And his investigation into go-to was key. He found that certain uses of go-to made it impossible to recursively break down programs into smaller, manageable units, which meant you couldn't mathematically prove they were correct.
Ah, so it hindered decomposition.
Exactly. But simple structures like if-then-else for selection and do allow for iteration.
Sequence, selection, iteration.
That'd be basics.
Right. Identified by Boom and Jacopini. Dexter realized these structures did allow programs to be broken down into provable units.
Okay.
This led to his famous 1968 letter, Go-To Statement Considered Harmful.
Sparked quite a debate, didn't it?
Oh yeah, a decade-long debate. But it firmly established structured programming as a cornerstone of reliable software development. And the core insight here is fascinating. Progress wasn't about gaining more power, but about bravely accepting discipline limitations.
Restricting ourselves. Yes. Those very control structures that made a module provable turned out to be the minimum set needed to build any program. So structured programming basically transformed programming from just an art into something more like a scientific process. It let us break down huge problems into small provable functions that we could actually test systematically, making complex systems way more manageable and reliable.
Okay, so structure brought discipline to control flow. What about the next big paradigm? Object-oriented programming. Oh!
Right. Oh, Uncle Bob argues this is discipline imposed upon indirect transfer of control.
Indirect transfer, like function pointers.
Exactly. Polymorphism. And his take challenges the simplistic definitions you often hear, like, is just combining data and function or modeling the real world.
Yeah, I've heard those.
He says the true power lies in making polymorphism safe and convenient, and that power gives architects absolute control over every source code dependency.
Absolute control. That sounds powerful.
It is. He focuses on what O actually contributed regarding those three magic words: encapsulation, inheritance, and polymorphism.
Okay, let's break those down from his perspective. Encapsulation.
Interestingly, he argues that C, which isn't an OO language, actually had perfect encapsulation
Yeah.
with things like struct point, defined in a header, but the implementation hidden in a source file. Users of the header had no access whatsoever to the implementation details. Perfect hiding.
Okay.
But then C++ came along and, he argues, broke this perfect encapsulation by requiring member variables to be declared in header files, which then necessitated hacks like public, private, protected to try and patch it up.
Wow, okay, so C++ weakened it?
In his view, yes. And then Java and C# abolished the header implementation split altogether, weakening encapsulation even more because everything's in one file.
That's a very contrarian view on encapsulation.
It is. And similarly for inheritance. He points out that C programmers could achieve inheritance-like behavior through trickery, like carefully ordering fields and structs so one could masquerade as another. OO just formalized it.
Okay, and polymorphism.
Again, he says polymorphism existed long before OO languages. It was achievable with pointers to functions, ever since the early von Neumann architectures, where code and data live together.
Right, you mentioned function pointers earlier.
Yeah. The standard C library functions, getchar and putchar, are classic examples. Their behavior is polymorphic. It depends on how stdin and stdou are configured. Could be a console, could be a file, could be a network socket, without changing the source code of the program using them.
So if all these concepts kind of existed before, what was the big deal with OO then? What did it really add?
That is the million-dollar question, isn't it? And the answer, according to Uncle Bob, is that OO made polymorphism much safer and much more convenient.
Safer and more convenient. Okay.
It got rid of all those dangerous manual conventions, those hard-to-track bugs that came with raw function pointers, and this enormous power, especially when wielded through dependency inversion.
DIP again, from Solid.
Exactly. It allows architects to achieve that absolute control over the direction of all source code dependencies we mentioned.
Okay, unpack that dependency inversion link again. How does OO enable that?
Think about a typical system. You have high-level policy modules, calling low-level utility modules. Normally, the source code dependency follows that call structure. High-level depends on low-level.
Makes sense.
Dependency inversion, using OO polymorphism, specifically interfaces or abstract classes, lets you flip that dependency. The high-level module defines an interface describing the service it needs. The low-level module then implements that interface.
So the low-level module now depends on the interface defined by the high-level one.
Precisely. The flow of control still goes from high-level to low-level, the call, but the source code dependency points the other way. It points inward, towards the abstraction defined in the higher layer.
Okay, I think I get it. The arrow flips.
The arrow flips, and this is incredibly powerful. It means your UI and your database, which are typically low-level details, they can become plugins to your high-level business rules.
Plugins, how so?
Because the business rules define interfaces like user repository or order view, And the database and UI layers implement those interfaces. The business rules don't depend on the specifics of MySQL or React. They depend on their own interfaces.
Which means you can swap them out.
You can swap them out. It enables independent deployability and developability. Changes to the UI or database don't force changes or even recompilation in the core business logic.
Yep.
Different teams can work on different layers independently. That's the power OO unlocked via safe polymorphism and dependency inversion.
Wow. Okay, that's a much deeper take on OO than just classes and objects.
Much deeper.
All right, so we've had structured programming discipline control flow, OO disciplines indirect control transfer. What about the third paradigm, functional programming?
Functional programming, FP. This one Uncle Bob defines as discipline imposed upon variable assignment.
Variable assignment, meaning?
Meaning its foundational concept is immutability, the idea that variables, once they're initialized, don't vary, their state doesn't change.
No changing variables. How does anything get done?
It's a different way of thinking. Instead of modifying state, you create new state based on old state. Let's take a simple example. Printing the squares of the first 25 integers.
Okay.
In, say, Java, you'd probably use a for loop with a variable I that you increment. I is mutable. Its state changes.
Right. I++.
Exactly.
Yeah.
Now, in a functional language like Clojure, you might do it like this. Println, take 25, map fnx, range.
Whoa. Okay. Looks different.
It does. But notice what's happening. Range gives you a sequence of numbers. Map applies a squaring function to each number, creating a new sequence of squares. It gets the first 25 elements of that new sequence, println displays them. Crucially, no variable state was ever modified. We just created new data based on transformations.
So it's all about transforming data, not changing it in place.
Exactly. And the architectural implications of this immutability are profound, really significant.
Such as?
Uncle Bob states it very clearly. All race conditions, deadlock conditions, and concurrent update problems are due to mutable variables.
All of them. Wow.
If no variable is ever updated, you simply cannot have a race condition or a concurrent update problem. It makes concurrency, which is a massive headache in modern multi-core systems, dramatically simpler.
That sounds almost too good to be true. What's the catch?
Well, the catch is practical reality. Perfect immutability can be challenging with finite memory and processing speed. Constantly creating new objects can be expensive.
Right. Performance concerns.
So compromises are often made. One technique is segregation immutability. You partition your application. Some parts are purely functional and immutable, while others, where state changes are necessary, are carefully contained and guarded.
Okay, contain the damage, so to speak.
Sort of. Another approach is event sourcing. Instead of storing the current state, like an account balance, you only store the sequence of events or transactions that led to that state, like source control does.
Like Git storing diffs.
Exactly. When you need the current state, you replay the events. With memory getting cheaper and processors faster, Uncle Bob suggests this idea of making applications entirely immutable is becoming increasingly practical. And it promises to eliminate some of the nastiest bugs we face, especially around concurrency.
Okay, so let's recap these paradigms. Structured, O, functional. What's the big picture takeaway?
The unifying theme really is restriction. Discipline.
Right. Each one told us what not to do.
Precisely. Structured said don't use arbitrary jumps. OO said don't manage polymorphism unsafely. Functional said don't mutate state carelessly. They didn't really add new fundamental capabilities that weren't technically possible before.
They just gave us guardrails.
Exactly. Guardrails. They taught us disciplined restraint, guiding us away from common pitfalls, leading to systems that are more robust, more understandable, and ultimately more manageable. It's a powerful lesson. True progress often comes from knowing what not to do.
All right, so those are the fundamental disciplines, the bricks in our building analogy. Now, how do we combine those into stable structures, like the walls and rooms of our software?
This is where the solid principles really shine. They operate at that mid-level, guiding us on how to arrange our code into components and modules that work well together.
Okay, solid, acronym time.
Yep. Coined by Michael Feathers based on principles Uncle Bob had been teaching. The goal of SOLID is to help us create software structures that, 1, tolerate change.
Adaptability again.
Always. 2, are easy to understand. And 3, form the basis of components that can be used in many software systems. Reusability.
And when we say class and solid, it's not just OO classes.
Yeah, it's broader. Think of it as any coupled grouping of functions and data. Any cohesive module, really.
Got it. Let's dive in. S, single responsibility principle, SRP.
SRP. This one is probably the most misunderstood of the bunch.
Yeah, how so?
People often think it means a function or a class should only do one thing, like one small task.
That's how I always thought of it.
It's a common interpretation, but it's not quite right. The principle actually states a module should have one and only one reason to change.
Reason to change. Okay, what defines a reason?
An actor,
Yeah.
a stakeholder, a group of users or business roles that care about that specific part of the system and might request changes to it.
So it's about who cares, not what the code does.
Exactly. It's about separating concerns based on the different groups of people who have a stake in those concerns. Think CFO, COO, DBA, those kinds of distinct roles.
Okay, give me an example.
All right, imagine a simple employee class in a payroll system. Maybe it has 3 methods:
Yeah.
calculate pay, report hours, and save.
Seems reasonable. All related to an employee.
On the surface, yes. But think about the actors. Who cares about calculate pay changing?
The finance department, the CFO's team,
Right. Who cares about report hours?
HR operations, the COO's team,
Probably. And who cares about how the data is saved?
the database administrators, the tech team, the CTO's group.
Exactly. 3 different methods, serving 3 different actors, all bundled together in one class. That class has 3 reasons to change. It violates SRP.
Huh. Okay, I see the distinction now. It's about the source of the change request.
Precisely. The true axis of change isn't always the technical function. It's often the business accountability. SRP shifts our focus there.
So what problems does violating SRP cause? What are the symptoms?
2 main ones. First, accidental duplication leading to unexpected breaks.
Okay.
Imagine both calculate pay and report hours happen to use some shared helper function, maybe called regular hours.
Seems plausible. They both need that info.
Right. Now, the CFO's team requests a change in how regular hours are calculated for pay purposes. A developer goes in, changes regular hours to satisfy the CFO.
And accidentally breaks the reports the COO relies on.
Bingo. The developer, focused entirely on the CFO's task, might not even realize they impacted the COO's team. This could lead to millions of dollars in damage from incorrect reports. I've seen things like this happen. It's scary how easy it is.
Yeah, that sounds like a nightmare. What's the second symptom?
Merge conflicts. Imagine the CTO's database team needs to change the save method to work with a new database version. At the same time, the COO's HR team needs to change report hours for a new regulation.
They're both editing the same employee.java file.
Exactly. For completely different reasons serving different actors. Now you have a merge conflict. And merges are risky. A mistake during the merge could break functionality for the CFO, the COO, and the DBA all at once.
Yikes. So SRP helps avoid these collisions.
It does. By separating code that different actors depend on, you isolate changes and minimize the risk of these costly hidden problems.
So what's the solution then, if you have that employee class?
The solution often involves creating more classes, which might seem counterintuitive if you're just counting lines of code or files.
You're right. Seems like more complexity.
But it's organized complexity. One way is to have a simple data structure, maybe employee data, with no methods at all, just holds the data.
Okay, like a plain old data object.
Exactly. And then you create 3 separate functional classes: pay calculator, hour reporter, employee saver. Each one takes employee data as input, performs its specific task, and is responsible to only one actor.
So you separate the functions from the data.
That's one way. Another popular way is using the facade pattern. You might still have an employee facade class, but its methods simply delegate the work to those specialized, single responsibility classes behind the scenes.
Okay. So the facade provides a simple interface, but the real work is separated underneath.
Precisely. The core goal is always to separate code that's responsible to different actors. Ensure each module is cohesive around a single reason for change. That prevents unintended consequences and makes the system much easier and safer to modify.
Makes sense. Okay, moving on to L. Liskov's substitution principle, LSP. This one sounds more formal.
It does. Named after Barbara Liskov. Her formal definition is a bit dense. If for each object O1 of type S, there is an object O2 of type T, such that for all programs P defined in terms of T, the behavior P is unchanged when O1 is substituted for O2, then S is a subtype of T.
Okay. Let's unpack that. Simpler terms.
Basically, if your code is designed to work with a type T, say a license, you should be able to pass in an object of any subtype S, like a personal license or business license, without the code breaking or behaving unexpectedly. The subtype must be perfectly substitutable for the base type.
So subtypes shouldn't break the promises made by the base type.
Exactly. A good example is that license class. If you have a billing application that processes license objects, it should work correctly whether you give it a personal license or a business license without needing to know the specific type.
Okay. What's a bad example? The classic violation.
The classic infamous violation is the square rectangle problem.
Ah, I've heard of this one.
Right. Logically, a square is a rectangle, so it seems natural to make square a subtype of rectangle.
Seems fine.
But it violates LSP. Why? Because a rectangle usually has methods like set width and set height that work independently. You can set the width to 5 and the height to 2. But a square must have equal width and height. So if you inherit set width and set height in your square class, how do you implement them? If set width 5 also sets the height to 5, it breaks the expectation of the rectangle's behavior.
Right, because if I have code expecting a rectangle, I might call set W5, then set H2, and then expect the area to be 10.
Exactly. But if you secretly passed in a square object, set H2 would probably also change the width back to 2, or set W5 change the height to 5 earlier. The area calculation would be wrong. The substitution broke the expected behavior.
Okay, that makes the principle clear. But how does this impact architecture? Seems like a low-level coding detail.
It seems like it. But even a seemingly small LSP violation can pollute a system's architecture with a significant amount of extra mechanisms.
How so?
Uncle Bob gives an example of an Acme taxi company system. Imagine your system integrates with multiple taxi dispatch partners. One major partner, Acme, uses a slightly different field name for the destination, say DEST, instead of the standard destination your system expects.
Okay, a minor naming difference.
Seems minor. But if you handle this by putting yes, driver.source, Acme, checks throughout your system wherever you access the destination.
Oh no, special cases everywhere.
Exactly. That little LSP violation, Acme's driver object isn't perfectly substitutable, forces you to litter your code base with special handling, making it fragile and much harder to maintain. Every time you touch destination logic, you have to remember the Acme case.
Yikes. So LSP helps ensure your interfaces and implementations allow for truly interchangeable parts, preventing that kind of pollution.
Precisely. It preserves the integrity and simplicity of your core logic by ensuring substitutability.
Got it. Okay, next up is dependency inversion principle, DIP. We touched on this with OO.
We did, and it's arguably the most architecturally significant of the solid principles.
Why is that?
Because it dictates the overall direction of dependencies in your system. The core idea is, the most flexible systems are those in which source code dependencies refer only to abstractions, not to concretions.
Abstractions, not concretions, meaning interfaces or abstract classes, not concrete implementations.
Exactly. High-level policies should not depend on low-level details. Instead, the low-level details should depend on abstractions defined by the high-level policies.
Okay, give me the practical coding rule again.
In practice, it means your import or using or include statements should point to interfaces or abstract classes whenever possible, especially across architectural boundaries. Your core business logic shouldn't import com.mysql.jdbc driver.
Right. It should import maybe com.mycompany.persistence.databasegateway.
Exactly. An interface that your application defines. Then your separate MySQL implementation module will implement database gateway and depend on that interface. The dependency is inverted against the flow of control.
And Uncle Bob has specific coding rules for this too, right? Like, don't refer to volatile concrete classes.
Yes, very specific.
Yeah.
Refer to abstract interfaces instead. Also, don't derive from volatile concrete classes and don't override concrete functions. Essentially, never mention the name of anything concrete and volatile in your high-level modules. These are strong guidelines to maintain that separation.
But wait, at some point, something has to create the concrete object, right? Like the actual MySQL database connector has to be instantiated somewhere.
Yeah.
How do you do that without violating DIP?
Excellent question. That necessary evil, the creation of concrete objects, is pushed to the outermost boundaries of the system, often using patterns like the abstract factory.
Ah, factories.
Right. The factory knows about the concrete classes, but the rest of the system only knows about the abstract factory interface and the interfaces of the products it creates. The factory becomes the one place that manages that undesirable dependency on concrete definitions.
So you isolate the dirty part.
You isolate the dirty part. Imagine that conceptual diagram again, with the curved line separating abstracts from concretes. The abstract factory pattern helps ensure all source code dependencies crossing that line point inward towards the abstract side against the flow of control. That's the essence of dependency inversion in action.
And the big payoff you mentioned earlier.
Independent deployability and developability. Because your UI and database are now plugins, depending on interfaces defined by your core business rules, changes in those outer layers don't break the core. Teams can work in parallel, deploy independently. It's a massive win for large or evolving systems. DIP is what makes true modularity possible.
Okay, wow. DIP is huge. What about interface segregation principle? ISP.
ISP is closely related to DIP and SRP. It's simpler, though. It advises software designers to avoid depending on things that they don't use.
Don't depend on things you don't use. Makes sense.
Imagine a big interfacer class called operations with, say, 3 methods, OP1, OP2, OP3. Now you have a client module, user1, that only needs to call OP1.
Okay.
If user1 depends on the entire operations class, it means that if OP2 or OP3 changes, perhaps because user2 or user3 needed a change, user1 might need to be recompiled or redeployed even though nothing it cares about actually changed.
Unnecessary coupling.
Exactly. ISP says, don't do that. Segregate the operations interface into smaller, more focused interfaces. Maybe user1 operations, which is OP1, user2 operations with OP, etc. Then user1 only depends on the tiny user1 operations interface.
So changes in OP2 or OP3 become completely irrelevant to user 1.
Completely irrelevant. It prevents unnecessary recompilation, redeployment, and reduces the surface area of dependencies. It keeps things lean and focused.
Got it. And finally, open-closed principle, OCP.
OCP. This one comes from Bertrand Meyer. It states that the software system should be open for extension, but closed for modification.
Open for extension, closed for modification. What does that mean in practice?
It means you should be able to change the behavior of your system by adding new code rather than changing existing code.
How do you achieve that?
Primarily through abstraction and polymorphism, the tools OO gave us. If you have a module that processes different kinds of shapes, instead of having a big ifelse of block checking the type of shape.
Which you'd have to modify every time you add a new shape.
Exactly. You define a shape interface with a draw method. Then each specific shape, circle, square, implements that interface. Your processing module just works with shape objects and calls draw. To add a new triangle shape, you just create a new triangle class implementing shape.
And you don't have to touch the original processing module at all.
Not at all. It's closed for modification, but open for extension via new implementations. This is fundamental for creating systems that can evolve gracefully without constant risky changes to core, stable code.
Okay, so we've got the foundational disciplines from Paradigms and the mid-level structuring guides from Solid. Now let's zoom out again to the whole building. What are components in this bigger picture?
Right, the units we actually ship and deploy.
Yeah.
Uncle Bob defines components very simply. They are the fundamental units of deployment.
Units of deployment? Like what?
Think of java.jar files, .NET DLLs, ruby.gem files, even shared libraries in CC++ data. They're the smallest pieces of the system that can be independently deployed, versioned, and potentially replaced.
Okay. The things you actually move around.
Exactly. And the way we handle these components has evolved dramatically over the history of software. It's a fascinating story in itself.
Yeah. Take us to it quickly.
Well, in the really early days, pre-1970s, programs often weren't even relocatable. If you wanted to use a library function, you often had to include its source code directly in your program.
Wow, so compile times must have been huge for a large program.
Hours, literally hours. Then we got separately compiled libraries, but they had to be loaded at fixed memory addresses. Still pretty inflexible.
Okay.
The 1970s brought linking loaders, allowing programs to be split into segments. Then came linkers proper in the 70s and 80s. They separated the slow linking process from the faster loading process, producing these linked relocatables. Getting better.
Getting more modular.
Definitely. And finally, as hardware got much faster in the 80s and onwards, we arrived at dynamic linking. Linking could happen quickly at load time or even runtime. This is the era of ActiveX, shared libraries, .jar files, DLLs.
The components we know today.
Right. And this half-century evolution, Uncle Bob points out, has made component plug-in architecture the casual default. We almost take it for granted now.
Plug-in architecture. Like mods for games.
Exactly. Think of Minecraft mods, just drop a custom .jar file in a folder. Or tools like ReSharper, plugging into Visual Studio via DLLs. We routinely ship and consume these dynamically linked files as plugins, allowing systems to be extended and customized in incredibly flexible ways. We've arrived at a place where building systems out of independent, deployable components is the norm, thanks to this long evolution.
Okay, so we have these deployable components. Now, what's the ultimate purpose of architecture when you consider the whole life cycle of a system built from these components?
That's the critical question. And the answer is not just to make the system work initially, because let's be honest. Systems with terrible architectures can still work, at least for a while.
Yeah, you can hack something together that functions.
You absolutely can. But the true costs, the real pain, emerge over the system's lifecycle. The ultimate purpose of software architecture, according to Uncle Bob, is to facilitate the development, deployment, operation, and maintenance of the system over its entire lifetime.
Facilitate the whole life cycle.
Okay, and the key strategy to achieve that facilitation is to leave as many options open as possible for as long as possible.
Keep options open. Don't paint yourself into a corner.
Exactly. It's a fundamental shift in focus. Good architecture isn't just about correctness. It's about minimizing those lifetime costs and maximizing programmer productivity by preserving flexibility.
Let's break down those life cycle costs. How does architecture impact, say, development?
Well, good architecture partitions the system into well-isolated, independently developable components. This directly supports larger teams working in parallel without stepping on each other's toes. It naturally aligns with Conway's law.
Ah, the idea that system structure mirrors the organization's communication structure.
Right. A good component structure facilitates effective team organization and parallel development.
Okay. What about deployment?
A good architecture aims for easy deployment with a single action. Think one-click deploy. However, this is where prematurely adopting certain patterns like microservices can backfire. If not done carefully, the deployment complexity can become daunting, completely overwhelming any development benefits. Architecture needs to consider deployability from the start.
Makes sense. Operation. Running the system day to day.
Interestingly, Uncle Bob argues this is often less critical architecturally than the other costs.
Really? Why?
Because hardware is cheap and people are expensive. If your system is a bit slow or inefficient in operation, you can often just throw more hardware at it. Buying more servers is usually less costly than massive developer effort trying to optimize poorly structured code.
Okay, so operational efficiency isn't the primary architectural driver. What about maintenance?
Maintenance. This, he says, is typically the most costly aspect of a system's lifecycle by far.
Why is that?
Two main reasons: spelunking and risk. Spelunking is that horrible process of digging through tangled, poorly documented code just to understand how it works or where to make a change. It eats up huge amounts of time.
Yeah, trying to decipher someone else's or your own mess from 6 months ago.
Exactly. And then there's the risk. Every time you touch that complex, tangled code, there's a high risk of introducing new, subtle defects somewhere else.
Breaking something unintentionally.
Right. A carefully thought-through architecture with clear component separation and stable interfaces vastly mitigates these costs. It makes understanding the code easier, less spelunking, and drastically reduces the risk of unintended consequences when making changes. Good architecture is fundamentally about controlling maintenance costs.
Okay, so that philosophy, leaving options open, how does that translate into actually drawing boundaries between these components?
It means strategically designing your system so that the less relevant components, things that are details like the UI or the specific database you're using, become plugins to your more relevant core components like your business rules.
Plugins again. So the details plug into the core.
Precisely. And this isn't even a new idea in computing. We learned this lesson decades ago with device independence.
Device independence. Tell me more.
Think back to the 1960s. Programmers used to bind our code directly to the I/O devices. If your program needed to print something, you wrote code specifically for that model of printer.
Wow. Tightly coupled.
Extremely. So when a customer decided to switch from using punch cards to magnetic tape for input,
You had to rewrite the program.
you had to rewrite large portions of the original program. It was a nightmare. The solution: we invented device independence. Operating systems started providing abstract interfaces for I/O devices. Your program talked to a generic card reader or line printer interface, and the OS handled mapping that to the actual physical device.
Ah, so the program was decoupled from the specific hardware.
Exactly. Same thing happened with disk storage. Uncle Bob tells a story about an accounting system in the early 70s that had specific disk cylinder, head, and sector numbers hardwired right into the code.
Oh my God. What happened when they upgraded the disk drive?
Disaster. It meant changing all the hardwiring everywhere. A wiser colleague suggested using relative addresses instead and having a single conversion routine handle the mapping to physical addresses, decoupling the high-level policy where the data logically was from the low-level detail, the physical disk structure.
So the lesson is the same. Abstract the details. How does this apply today with databases and UIs?
It applies directly. Just like those old physical devices, the specific database system you choose, its particular query language, even its schema, these are technical details. They change independently of your core business rules or your UI presentation logic.
So the architecture must separate them.
It absolutely must. You make the database a plug-in to the business rules, you make the UI a plug-in to the business rules. This separation prevents changes in those volatile outer layers from constantly disrupting your stable core. Think about it. If your core business logic is littered with SQL statements specific to Oracle, what happens when you want to switch to PostgreSQL?
A massive, painful rewrite.
Exactly. But if your business logic only talks to a repository interface, you just write a new PostgreSQL implementation of that interface. The core remains untouched.
Uncle Bob uses that analogy of ReSharper in Visual Studio, right?
Yeah, it's a great analogy for the asymmetry we want. ReSharper's source code depends heavily on Visual Studio's APIs. It plugs into VS.
Right.
This creates a deeply asymmetric relationship. JetBrains, who make ReSharper, can't really harm Microsoft's core VS product with their code. But Microsoft could, if they change their APIs significantly, break ReSharper.
Okay, so the plugin is vulnerable, the host is protected.
Exactly. We want that same immunity in our systems. Our core business rules shouldn't break just because someone redesigned a web page or the DBA decided to refactor the database schema. By arranging our system as a plugin architecture, with details plugging into the core, we create these firewalls. Changes can't easily propagate inward from the volatile outer layers to the stable center.
So, given we need these boundaries, where exactly do we draw them? How do we decide what's core and what's a detail?
The answer, quite elegantly, comes back to the single responsibility principle. SRP again.
Ah, reasons to change. Actors.
Precisely. Boundaries are drawn where there is an axis of change. Components that change at different rates, or for different reasons, meaning for different actors, should belong on opposite sides of an architectural boundary.
So if the UI changes frequently because the marketing team wants new layouts, but the core calculation logic is stable,
you draw a boundary between them. If the database schema changes because the DBAs are optimizing storage, but the business rules themselves haven't changed.
boundary, keep them separate.
Exactly. SRP, thinking about who causes change and why, becomes your primary guide for identifying where to place those critical architectural boundaries.
Okay, so we've identified where the boundaries should be. How do we actually implement them? Are there different ways?
Yes, absolutely. And this offers huge flexibility. Uncle Bob talks about different decoupling modes for implementing these boundaries. They're basically 3 levels.
2 levels, okay.
First, source-level decoupling. Think of Ruby gems or C++ header files. You control the source code dependencies, maybe using interfaces, but everything ultimately gets compiled and runs together in the same address space.
Often called a monolithic structure, right?
Yeah, that's the common term. Simple to deploy, but less isolation. Second, deployment-level decoupling. Here, components are separate deployable units, like Java.jar files or .NET DLLs. They might still run in the same process sometimes, but they are packaged and deployed independently. Communication between them might involve slightly more expensive OS calls or data serialization.
Okay, more separation. What's the third level?
Third is service-level decoupling. This is the strongest boundary. Think microservices. Each component runs in its entirely separate process, potentially on a different machine. They communicate over the network, usually via HTTP calls or message queues. Every execution unit is entirely independent.
Maximum isolation, but also maximum communication overhead, potentially.
Exactly. There are trade-offs. And what's really clever, and a key part of clean architecture, is that the best mode isn't fixed. It might change over a project's lifetime.
Oh.
Yeah. Maybe you start with a monolith, source-level decoupling, for simplicity, but you design it with clear boundaries internally, using interfaces, DIP. Later, if needed, you can relatively easily pull some components out into separate deployable units, deployment level, or even into separate services, service level, without rewriting the core logic, because the boundaries and dependencies were already clean.
So a good architecture leaves the decoupling mode open as an option.
Precisely. He tells the story of Fitness, his testing tool. The web server part and the wiki engine part were designed from the start with clean boundaries, intending that they could be separated later if someone wanted to reuse just the wiki engine, for example.
Okay.
But for initial release, they deployed them together in a single .jar file. Why?
Yeah.
For download and go, simplicity for the users. It was the easiest deployment option at that time. They deferred the more complex deployment decision.
Did anyone ever separate them?
Years later, a customer actually did. They wrote their own front end that talked to the Fitness wiki engine using the existing boundary, proving the flexibility was real. This kind of anticipatory design Keeping future deployment options open, even if you don't use them immediately, is a hallmark of clean, resilient architecture.
That's a great story. Now, one more potential pitfall when drawing boundaries or structuring components: duplication. Architects seem terrified of duplicated code. DRY, don't repeat yourself, is like a mantra.
It is, and often for good reason. But Uncle Bob cautions that not all duplication is inherently bad. We need to distinguish true duplication from false or accidental duplication.
True versus false duplication. Okay, what's the difference?
True duplication is when you have two identical or very similar pieces of code, and if one of them needs to change for a specific reason, the other one must change for the exact same reason. They are fundamentally linked. This is genuinely bad and should usually be eliminated by creating a shared abstraction.
Okay, that makes sense. What's false duplication?
False or accidental duplication is when two pieces of code happen to look similar right now, but they exist for different reasons, serve different actors, or are likely to evolve along different paths in the future.
Ah, so they look the same by coincidence, but they aren't conceptually linked.
Exactly. For example, imagine you're vertically slicing your application by use case. You might find that the screen for adding a new customer and the screen for editing an existing customer have very similar layouts and fields today.
Okay.
The temptation is huge to create a single shared component or template for both screens to avoid repeating the HTML or UI code.
Seems like good DRY practice.
But if the add customer workflow is likely to diverge significantly from the edit customer workflow over time, maybe adding different validation rules, different required fields, different helper widgets, then forcing them to share code now creates a rigid coupling. When the requirements inevitably diverge, changing the shared component for one use case might break the other. This is accidental duplication, and Uncle Bob advises you should resist the temptation to commit the sin of knee-jerk elimination of duplication in these cases. It's often better to keep them separate, even if they look similar initially.
So sometimes repeating yourself is actually the cleaner option in the long run.
It can be if the duplication is accidental rather than true. Similarly, don't just pass a raw database record object directly to your UI layer. Even if the fields currently match exactly what the UI needs, create a separate view model object. Why? Because the database record represents the persistent structure, serving the DBA actor, while the view model represents the presentation structure, serving the UI/UX actor. They have different reasons to change, even if they look the same today. Violating the separation due to apparent duplication leads to coupling problems down the line.
All right, let's try and pull all these ideas, paradigms, solid principles, boundaries, components together into the specific clean architecture model that Uncle Bob proposes. He talks about screaming architecture. What does he mean by that?
Yeah, screaming architecture. It's a great phrase. The core idea is that your architecture should immediately tell you what the system does, not what technologies it uses.
So the use cases should be obvious.
Yeah. Exactly. A good software architecture allows decisions about frameworks, databases, web servers, and other environmental issues and tools to be deferred and delayed. It should scream about the use cases of the application.
Okay. Like house blueprints.
Precisely his analogy. You look at blueprints, they scream about the living room, the kitchen, the bedrooms. They don't scream, this house is made of bricks, or this house uses PEX plumbing. Those are details.
Right. The purpose is clear, the implementation is secondary.
Exactly. So your software architecture should scream order entry system or content management platform, not Spring Boot application, or React front end with a MongoDB backend.
So frameworks are just tools in this view, not the architecture itself.
Absolutely. Frameworks are powerful, yes, but they are tools. They're not architectures you should conform your application to. Architects need to look at each framework with a jaded eye, developing strategies to prevent those frameworks from dominating the core architecture and polluting your business logic. Keep them at arm's length.
And one big practical benefit of doing this, making the architecture scream about use cases.
Testability. It's a massive win. If your architecture truly emphasizes the use cases and keeps frameworks pushed out to the edges,
then you should be able to test the core without them.
bingo. You should be able to unit test all those use cases without any of the frameworks in place. Imagine testing your critical business logic, your order processing, your calculation engines without needing a web server running or a database connected and seeded with data.
That sounds like a dream for development speed and reliability.
It is. Your core entity objects should just be plain old objects, no framework dependencies. Your use case objects coordinate these entities. All of it testable in complete isolation. This intrinsic testability is a huge advantage, accelerating development cycles and drastically reducing the cost and effort of finding and fixing bugs. You can swap out the real database or UI with simple test doubles.
Okay, so how is this visually represented, the concentric circles model?
Right, the famous onion diagram, the concentric circles. It's a way to visualize the separation of concerns and the dependency rule. While the book doesn't have the exact diagram, the description implies it clearly.
Let's walk through the layers from the inside out. What's at the very center?
At the innermost circle, you have entities. These encapsulate the enterprise-wide critical business rules. These are the most general, high-level rules of the business domain itself, the concepts least likely to change when something external like the UI or database changes. Think product, order, customer. The entity is pure business logic and data, nothing else. No framework code, no UI code, no database code.
Okay, pure business core. What's the next layer out?
The next layer is use cases, sometimes called interactors. These contain the application-specific business rules. They orchestrate the flow of data to and from the entities to implement the specific use cases of the system, like place order or add product to catalog. They know about entities, but they're still isolated from external concerns like the UI or database.
So use cases implement the application's workflows using the core entities. Got it. Layer 3.
Layer 3 is interface adapters. This is a crucial layer. It's a set of adapters that convert data between the formats convenient for the inner circles, entities, use cases, and the formats convenient for the outer circles, like the database, the web, external APIs.
Conversion and adaptation. What kind of things live here?
This layer is where things like the model view controller and VC or model view presenter, MVP patterns reside. Your controllers, presenters, views, or view models, and also your database gateways or repositories implementations often live here. They adapt requests from the outside world into calls to the use cases and adapt the results from use cases back into formats suitable for the outside world.
Okay, so the presentation logic and data access logic adapters are in this layer. What's the final outermost layer?
The outermost layer is frameworks and devices. This is where all the details live. The specific web framework, like Spring Boot, Rails, Django, the specific database, MySQL, Mongo, etc., UI frameworks, React, Angular, external third-party APIs, device drivers, etc., all the concrete implementations and external dependencies are pushed out here.
And the golden rule governing these layers?
The dependency rule. We keep coming back to it. All dependencies cross the boundary lines pointing inward.
Always inward, never outward.
Ever outward. This means inner circles must never know anything about outer circles. Your entities cannot know about your use cases. Your use cases cannot know about your presenters or database gateways. Your interface adapters cannot know about the specific web framework or database you're using.
So your core business rules, entities, use cases, are completely ignorant of the database you use, or whether it's a web app or a console app.
Completely ignorant. It's like a one-way mirror. The outer layers depend on interfaces defined by the inner layers, but the inner layers have no clue what specific implementations exist in the outer layers. This ensures that changes in those volatile outer layers, a new web framework, a database upgrade, cannot break your stable inner core.
Okay, and how does data flow across these boundaries then, if the inner layers can't know about the outer ones?
Through simple data structures and transformation. When data needs to pass across a boundary, it's always transformed into the format that is most convenient and simplest for the inner circle receiving it. You don't pass complex framework-specific objects inwards.
Can you give an example, like that web system scenario?
Sure. Imagine request comes into a web controller, interface adapter layer. The controller unpacks the HTTP request data into a simple, plain input data object, maybe just strings, numbers, booleans. It passes this input data object inward across the boundary to the appropriate use case layer.
Okay, simple data crosses inwards.
Right. The use case does its work using entities and returns a simple output data object back to the controller, or usually to a presenter.
Also simple data crossing outwards.
Exactly. Then the presenter, still in the interface adapter layer, takes that output data and transforms it into a view model object. This view model is another simple data structure, specifically formatted for the view to display. It might contain formatted strings, flags for visibility, etc., but no complex domain objects or business logic.
So the view model is tailored just for the UI.
Precisely. It contains simple types like strings and booleans. No fancy date or currency objects from the domain layer. This keeps the view itself humble. The view's job becomes incredibly simple. Just take the data from the view model and render it. Almost no logic resides in the view itself.
This idea of keeping things humble seems important. You mentioned the humble object pattern.
Yes, the humble object pattern is a powerful way to think about and implement these boundaries. Its purpose is to identify and protect architectural boundaries by separating behaviors into two parts, one that's hard to test and one that's easy to test.
Hard to test versus easy to test.
Okay, the hard-to-test part is made as simple, humble as possible. The easy-to-test part contains the actual logic.
Like the presenter and view example.
Exactly. GUIs are notoriously hard to unit test directly. So, you make the view the humble object. You strip almost all logic out of it. Its only job is to passively display data given to it by the presenter, and maybe forward raw user input events. All the complex logic formatting data, handling user input, making decisions, resides in the presenter, which is easy to test because it doesn't depend directly on the GUI framework. It just works with simple data objects, like the view model.
So you push the complexity into the testable object and keep the boundary object, the view, simple.
Precisely. And this pattern applies elsewhere too. Think about database access. The code that actually interacts with the database executes SQL and maps results. That can be hard to test without a real database.
Right. Slow and requires setup.
So the implementation of your database gateway interface, the part that uses SQL or an ORM, becomes the humble object. The use cases or interactors that use the gateway interface contain the core logic and are easily testable because you can replace the real gateway with a simple test stub or mock.
Ah, so the ORM itself can be seen as a humble object boundary.
In a way, yes. It separates your gateway interface from the messy details of database interaction. Same goes for talking to external services. You can have a service listener that acts as the humble object, just handling the raw network communication and data conversion, while the testable object behind it handles the actual business logic based on the received data. It's a consistent strategy for maintaining testability across architectural boundaries.
Okay, we've covered a lot of principles and patterns, but to really make these stick, there's nothing quite like seeing how they play out in the real world, right? Especially when things go wrong.
Absolutely. Experience is the best teacher, even with someone else's experience.
And Uncle Bob's book is great for this. His architecture archaeology section digs into lessons learned over his, 5 decades in the industry?
Yeah, it's full of gems and painful lessons sometimes.
One of the biggest recurring themes seems to be the database is a detail.
Yes. Repeat it until it sinks in. From an architectural perspective, the specific database system, Oracle, MySQL, Postgres, Mongo, whatever, is a low-level implementation detail. The data model, the way you structure the information conceptually, that is architecturally significant.
Yeah.
But the engine that stores and retrieves it, a detail.
Why have relational databases been so dominant for so long then, if they're just a detail?
History and physics, mostly. Uncle Bob explains it really well. Their dominance came directly from the slowness of rotating magnetic disks, which were the primary way we stored bulk data for decades.
Disks are slow, milliseconds versus nanoseconds for RAM, right?
Exactly. That's a huge difference. Relational database management systems, RDBMS, evolved with all their complex machinery indexes, caches, query optimizers, specifically to mitigate that disk latency, to make accessing data on slow disks reasonably efficient.
So they were a solution optimized for a specific hardware limitation.
Precisely.
Right.
Which leads to his thought experiment. What if there were no disks? What if all data always lived in fast RAM?
Would we still use tables and sequence?
Of course not. We'd use the data structures programmers naturally reach for in memory. Linked lists, hash tables, trees, queues, stacks, whatever fits the problem best.
Right.
This really highlights that the database, particularly the RDBMS, is primarily just a mechanism to move the data back and forth between the surface of the disk and RAM. Its internal structure is optimized for disk I/O, not necessarily for the way your core business logic wants to think about the data.
And he shares a story about this, right? The T1 telecom system.
Yeah, great anecdote from the late 80s. They were building this system that inherently didn't need a relational database. Its data structures were best represented using trees and linked lists stored in simple random access files. Worked perfectly.
Okay,
But the marketing manager and a hardware engineer insisted they had to add an RDBMS. Why? Because customers expected it. Even though the system had few content-based relationships that would actually benefit from it, Uncle Bob fought him tooth and nail against adding it.
Joe, who won?
In the short term, Uncle Bob lost the argument. They added the RDBMS.
Ooh.
But the hard lesson learned, which he freely admits, is nuanced. He was right on the engineering principles. The system didn't need the RDBMS, But he was wrong in the context of the business reality at the time.
Because customers demanded it, even irrationally.
Exactly. It had become an irrational, external, and entirely baseless need, but it was no less real. The market demanded the checkmark feature.
So what's the architectural takeaway if you face that kind of external pressure? Compromise the core.
No, that's the key. If an external detail like that is unavoidable, the pragmatic solution is to bolt an RDBMS on the side of the system. Create a narrow, well-defined interface, a safe data access channel to interact with it, but maintain the core application's natural, optimal data structures internally. Don't let that external pressure pollute and distort your core architecture just to satisfy an external checklist item. Insulate the core.
Insulate the core. That seems to be the recurring theme. And it applies to the web too, right? The web is a detail.
Another huge one, yes. The web, he argues, is just the latest in a series of oscillations in computing that have been going on since the 1960s. A pendulum swinging back and forth between centralized computing, mainframe servers, and distributed computing power, smart terminals, PCs, rich clients.
So the web isn't fundamentally new, architecturally speaking.
Not really. It's fundamentally an I/O device, a way to get input from users and display output to them. And just like we learned with printers and disks, applications should maintain device independence from the specific I/O mechanism.
He traces the pendulum swings, right? Dumb terminals to mainframes.
Yeah, then smart terminals, then client-server architectures, then the web itself started swinging. Thin clients, pure HTML, then applets bringing code to the client, then Web 2.0 with AJAX and heavy JavaScript on the client. Now maybe Node.js pulling JavaScript back to the server.
It just keeps swinging back and forth.
It does. The web didn't change anything at all in the grand scheme of architectural principles. It's a delivery mechanism, a detail that should be pushed away from your core business rules, kept behind an insulating boundary.
He mentions companies struggling with this.
Yeah. Company Q agonizing over how to webify their existing desktop application. And Company A, whose mobile app UIs all broke overnight because the phone's OS vendor forced an update, changing the standard UI look and feel.
Ouch. Why do we keep making this mistake of coupling the UI tightly to the core?
Because it often seems easier in the short term. But it creates fragility. Architects must keep their UI and business rules isolated from each other to prevent the whims of presentation technology from constantly breaking the stable core logic.
So the final verdict.
The GUI is a detail. The web is a GUI. Therefore, the web is a detail. As an architect, your job is to put details like that behind boundaries, keep them separate from your core business logic, and embrace device independence. It's the same lesson we learned 50 years ago.
Okay. Databases are details. The web is a detail. What about frameworks? Surely they're more fundamental.
Nope. Frameworks are details too. Powerful tools, yes. Architectures, no. They should be treated as implementation details.
But frameworks often feel like they define the architecture, don't they? Especially big ones like Spring or Rails.
They often try to, and that's the danger. Uncle Bob uses that fantastic asymmetric marriage analogy.
Asymmetric marriage.
Yeah. Framework authors often urge you to couple your application to the framework as tightly as possible. They encourage you to inherit from their base classes, embed their annotations or decorators deep within your business objects, import their utility classes everywhere. They want you to fully commit.
Okay. Yeah. Seems convenient sometimes.
It can seem convenient, but the framework author makes no commitment to you whatsoever. They can change the framework in the next version, deprecate features you rely on, or even abandon the framework altogether. You, the application developer, bear all the risk and burden of that coupling. The marriage is entirely one-sided.
I never thought of it that way. So coupling tightly to a framework is risky.
Very risky. Frameworks often violate the dependency rule by design, forcing their way into the inner circles of your architecture. And what happens if you outgrow the framework's capabilities? Or it evolves in a direction that doesn't suit your needs? Or just a much better framework comes along?
You're stuck. It's hard to switch.
Once that wedding ring is on your finger, it's very hard to break away. Divorce is painful and expensive.
So what's the solution? Avoid frameworks altogether.
No, not necessarily. Frameworks can provide huge productivity boosts. The solution is, don't marry the framework. Use it, yes. Leverage its power. But keep it at arm's length. Treat it as a detail that belongs in one of the outer circles of your architecture.
How do you do that practically?
Use it primarily at the boundaries. For example, use a dependency injection framework like Spring, but only in your main component or your outermost composition root, the dirtiest, lowest level component, whose job is specifically to assemble the application and manage those external dependencies. Don't let Spring annotations or APIs leak into your core domain entities or use cases. Keep the core pure and framework agnostic.
Okay. But some frameworks seem unavoidable, right? Like maybe the standard library of your language?
True, some things, like the C++ standard template library or the Java standard libraries, are effectively inescapable marriages. But those should be conscious decisions, well-understood commitments to stable foundational platforms, not accidental entanglements with volatile third-party application frameworks.
Makes sense. Let's dig into some more of those architecture archaeology case studies. They're really illustrative. What about Fortel Micro?
Fortel Micro. This is a fantastic story from the late 1970s. They were moving a system from large mini-computers down to tiny 8085 microcomputers. And how did they manage components and deployment?
Wow.
They literally burned their code onto EEPROM chips, or erasable programmable read-only memory.
Okay, old school hardware.
Very old school. And then they plugged those individual chips into sockets on the main circuit board. Each chip contained a specific part of the system's functionality.
So each chip was an independently deployable component.
Exactly. You could fix a bug in one part of the system, burn a new EEPROM chip, pull the old chip out of its socket, and plug the new one in. They had effectively invented polymorphic dispatch and objects through this physical plug-in architecture years before the terms were common in software. It's a beautiful example of clean separation of concerns manifesting even in the physical hardware layout.
Wow, that's amazing, a physical plug-in architecture. What about the opposite? The rigid dispatch code story?
Yes, a cautionary tale. Mid-70s, a telephone system. One programmer, apparently brilliant but obscure, wrote the core dispatch determination logic, the code that figured out which repair crew should go where.
Okay. Critical logic.
Absolutely critical.
Huh.
But the code was incredibly dense, complex, and utterly incomprehensible to anyone else on the team. Nobody understood this code.
Uh-oh.
Yeah. Every time we tried to add a feature or fix a defect, we broke it. It was too fragile, too complex to touch safely.
So what did they do?
Eventually, management just threw up their hands and simply told us to lock that code down and never modify it. That code became officially rigid.
Wow. So a core piece of functionality just became unchangeable because it was too complex.
Exactly. It powerfully demonstrates how seemingly brilliant individual effort, if not clear and understandable, can become a massive architectural liability. It underscores the immense long-term value of clean, simple, maintainable code over opaque genius, no matter how clever it seems initially.
That's a sobering lesson. Then there's the clear startup story from the 80s. Sounds like Uncle Bob's own early experience.
Very much so. He describes the typical startup chaos.
Architecture.
Are you joking? This was a startup. We didn't have time for architecture. Just code, damn it. Code for your very lives.
Haha. Sounds familiar.
Right. They just built huge castles in the air, including a monstrous 3,000-line C function, ominously named G, the graphic interpreter.
3,000 lines in one function. Yikes.
Yikes indeed. After 3 years of frantic coding and, crucially, no sales, the company was struggling. This period of failure, dealing with the consequences of neglecting architecture and getting tangled up in a big, slow, intrusive, expensive third-party framework, a database they probably didn't need, was formative for him. It's when he started learning C++C, digging into object-oriented principles from pioneers like Grady Booch, debating on Usenet newsgroups. Basically, the experiences that forged him into Uncle Bob. It highlights the hard-won lessons learned from the just code mentality.
Failure is a great teacher again. Lastly, the Architect's Registry Exam Project. What was the lesson there?
This was early 90s. He and Jim Newkirk were building a system to automate architecture registration exams. It involved 18 different CAD-like GUI applications for the exams and 18 corresponding scoring applications. A lot of similar but distinct parts.
Okay. Sounds like a perfect candidate for a reusable framework.
Exactly what they thought. So they decided to build a reusable framework first, before building the actual application.
How did that go?
Not well. After a year, they had 45,000 lines of framework code and only 6,000 lines of actual application code. And the framework they'd built, it wasn't particularly reusable for the next 17 applications anyway. They'd over-engineered it based on speculation.
Ouch. A year wasted.
Pretty much. They had to significantly rethink and rewrite.
Yeah.
The hard-won lesson was profound. You can't make a reusable framework until you first make a usable framework.
Usable first, then reusable.
Right. Reusable frameworks require that you build them in concert with several reusing applications. You need the feedback from real-world use cases to guide the design of the reusable parts. You can't just design reuse in a vacuum based on theory. It underscores the need for pragmatic, Iterative evolution of design, not grand, speculative, upfront framework building. Hashtag tag up, outro. So after digging through all of this, the history, the principles, the patterns, the war stories, what's the ultimate takeaway from this deep dive into clean architecture?
Yeah, what's the core message?
I think it's that the fundamental rules of good software architecture are, maybe surprisingly, timeless and changeless. They don't really depend on the latest technology fad.
Because the underlying problems don't change much.
Exactly. The core principle is always about designing systems that are supremely adaptable. Systems where your high-level policies, your core business logic, are carefully insulated from the low-level details, the database, the UI, the frameworks. It's all about deferring decisions, keeping options open, enabling independent development and deployment, and fundamentally protecting the true softness, that ability to change of your software from the relentless march of technology and shifting market demands.
Building things that can bend without breaking.
Precisely. Building systems that gracefully evolve rather than painfully breaking under pressure.
And this isn't just abstract stuff for software engineers, is it? We talked about universality earlier.
Definitely not just for coders. Think about your own work, your own domain, your organization, even personal projects, where you may be making premature, high-level commitments to low-level details, locking yourself in too early.
Good question.
What are the axes of change in your projects? The things that change at different rates or for different reasons. Could you use those axes to draw clearer boundaries, to decouple things better? How can you apply these principles of discipline, separation of concerns, dependency inversion to make whatever you're building more resilient, less fragile, and ultimately more valuable in the long run?
It's about seeing the bigger picture, the structure, not just the immediate task. Building the forest to last, not just planting trees haphazardly.
Well said. And maybe one final provocative thought to leave people with. Robert C. Martin makes that point about the basic building blocks of software: sequence, selection, iteration, and indirection, like polymorphism or function pointers.
Right. Been the same since Turing in 1946.
Pretty much. So in a very profound way, what we've truly learned over the last, say, half-century plus in software isn't really revolutionary new ways to do things. It's mostly been about learning what not to do.
Learning through mistakes. Identifying the patterns that lead to messes.
Exactly. The entire quest for clean architecture, for timeless design principles, is fundamentally a quest for disciplined restraint. Knowing what not to couple, where not to introduce dependencies, what decisions not to make too early. It's the discipline to keep things simple, separated, and flexible.